It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good afternoon, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we are going to look at the standard model of physics, as well as classifications of matter. Before you start taking notes, I'd recommend that you fast forward through this video, because we're going to make a graphic organizer to organize all our information. So this will give you a better layout of what your notebook should look like. We're going to start with the classifications of matter. We've talked about an atom, as well as protons, neutrons, and electrons. Well, today we're going to talk about subatomic particles. So those are particles that make up the protons and neutrons. So there are particles smaller than protons, and that's what makes up a proton. So the particles that create a proton or make up a proton are called quarks. And it turns out that there are 3 quarks that make up a proton. So the first thing we're going to talk about are elementary particles that are made up of 3 quarks. And one of those elementary particles are protons. So the first thing we'll look at are protons. And we recall that the charge of a proton is +1 elementary charge. So if we look at quarks in our Regents reference table, we could see that there are different types of quarks. And they come with different charges. There's an up quark, it's +2/3 elementary charge. A charm quark and a top quark, also +2/3 elementary charges. And then there's a down quark, a strange quark, a bottom quark, and those are all -1/3 elementary charges. So in order to make up a proton, and we know that they're made up of 3 quarks, these elementary charges are going to have to add up to +1 elementary charge to give us a proton. It turns out that protons are made up of up and down quarks. So a combination of the ups and downs will give us +1e. And if we do the math, we could see that +2/3 plus 2/3 minus 1/3 gives us +1. So a proton, sorry, we should have boxed that. A proton is made up of an up quark, and a down quark. And that's +2/3 elementary charges, +2/3 elementary charges, and then the down is -1/3 elementary charges. So the combination of an up-up-down quark gives us a proton. And then we also have neutrons inside the nucleus of the atom. So 3 quarks also make up neutrons, which has a total net charge of 0 elementary charges. So if we look at our Regents reference table again, a neutron is also made up of up and down quarks. And in order to get 0e, we're going to have a down quark, and an up quark. So a neutron is made up of a down quark, and an up quark. And if you look at their charges, they're negative 1/3 elementary charges, negative 1/3 for the other down, and then again the up is positive 2/3 elementary charges. And those all add up to 0 elementary charges. Anything that is made up of 3 quarks, we could give them their own name, and that's a baryon. So a baryon is just a combination of 3 quarks. Or in this case, a proton or a neutron could be a baryon. Now, if we look at our reference table closely, under the notes section, it says for each particle, there is a corresponding antiparticle with a charge opposite that of its associated particle. So for every up quark, there's an anti-up quark, which has a charge of negative 2/3 elementary charges. For every top quark, there's an anti-top quark, and its charge is negative 2/3 elementary charges. Also for the negative 1/3, for every bottom quark, there's an anti-bottom quark, and its charge is positive 1/3 elementary charge. So for every particle, there's a corresponding antiparticle. And we could look at particles that are also made up of quarks, and they are made up of a quark and an antiquark. So we also have particles that are made up of a quark, and we'll look at those later, plus an antiquark. And any particle that's made up of a quark and an antiquark, we're going to call a meson. So quarks and antiquarks is a meson. And then lastly, with quarks, anything that's made up of a quark, so either a meson or a baryon, is called a hadron. So these mesons and baryons, they are classified as hadrons. If we go back to our standard model physics in our reference table, we can see that we also have electrons. And there's no subatomic particle that makes the elementary charge, the elementary particle electrons. But there are other forms of electrons, or other forms of charges that have -1 elementary charge. That's a muon or a tau. So anything that's made up of electrons are called leptons. And then we also have these other particles that are called neutrinos. And there's 3 types of neutrinos: an electron neutrino, a muon neutrino, and a tau neutrino. All 3 of these particles have a net charge of 0 elementary charges, and they are also massless. Now these particles are mostly formed from stars, especially from, we could say, from our sun. And when the sun is fusing hydrogen particles together to give us helium, the byproduct of hydrogen fusing into helium are neutrinos. So every second, there are trillions upon trillions of neutrinos that are bombarding Earth. What happens in the sun is that the protons and hydrogen atoms are getting smushed together through the gravitational pull of the sun. And as they get smushed together, the protons are going to fuse together. And through a process we'll look at later in the college class, through a process of nuclear fusion, they're going to release the neutrinos as helium atoms are formed. So, anyways, we can also have elementary charges, or elementary particles, that are made up of electrons, and any of the three forms of neutrinos. Electrons we know have a charge of -1 elementary charge. Neutrinos, 0 elementary charges. And these combinations, or anything that's an electron or a neutrino, is called a lepton. And then lastly, the combination of leptons and hadrons gives us matter. So all the matter in the universe is simply composed of hadrons and leptons. Before we look further at the standard model of physics, I just want to write down what antiparticles are and just do a few examples. So we could say, and this is right in your reference table, for every particle, there is an antiparticle. With the same mass but opposite charge. So we said that for a for a top quark, it has a charge of +2/3. So for instance, a top quark is capital or lowercase t. Its charge is +2/3 elementary charges. An antitop would be a lowercase t with a bar above it, and its charge is -2/3 elementary charges. So anything that's an anti is just going to have a bar above it and the opposite charge. Now an electron or an anti-electron has a special name. So an anti-electron, which would be an E with a bar above it, we call a positron. Oops. So a positron or an anti-electron would be a positive electron, which means it has +1 elementary charges, but it still has the same mass as an electron. So it's an electron with a positive charge. Now you might be wondering, if we are made up of matter, why is it that we're not made up of antimatter? Or why aren't we made up of anti-electrons, anti-quarks, and anti-protons? Well, we have to remember that matter is just something that we defined as, and we defined it as a proton being +1e, an electron being -1e. But matter is just a name of something that we've defined as, so it can be possible that we're really made up of antimatter, but we just call it matter. You might also be wondering what happens if we take matter and smash it with antimatter. So for instance, if we took matter, or we'll call it pasta, and we smash pasta with antipasta, what would happen? So if these two particles collided with each other, they're going to annihilate each other and release tremendous amounts of energy. Or if we took a proton and smashed it with an antiproton, it would also annihilate and release a lot of amount of energy. Okay. So here's the standard model in physics for the Regents reference table. And then here's the classifications of matter. Notice it's backwards than what I did. But let's look at a more simplified or more elegant picture of the standard model of physics that organizes it a little bit better for us. In the purple section, we have our quarks. And there are 6 different types of quarks. In the green section, we have electrons and neutrinos, and there's 6 types of those. And then going vertically, we have what are called force carriers. We'll look at that in a second. And then also in yellow, we have the Higgs boson. So let's look at another chart that gives us perhaps a better idea of what all of these particles do or perform. Let's look at force carriers for different forces, and we'll start with the electromagnetic force. We saw previously that a photon is either being absorbed or emitted from electrons, and that's what's binding electrons within the atom. Otherwise, they would get sucked up into the nucleus due to the electrostatic force. So photons are the force carriers that allow the electromagnetic force to work, or that allow electrons to stay around the atom. There's an idea or a thought that for gravity, which binds or which is the attractive force, that there must be a photon or force carrier that allows the force of attraction to work. And this carrier is called the graviton. And as we can see, it hasn't yet been observed, but there are experiments that are being performed today to determine whether or not gravitons exist. And then we know that within an atom, in the nucleus of an atom, there are protons and neutrons, and those protons and neutrons are made up of quarks. And we saw previously that the protons, because they're similar charges, want to push each other away or oppose each other, so there must be a force that's binding the protons and neutrons together. And the protons and neutrons are made up of quarks, and the force that's binding them together is the strong nuclear force. But it's the gluons, which are gluing the quarks together, that keeps them bound. So inside or within the ups and down quarks, there are gluons, which have to do with the energies, or which requires an immense amount of energy to keep them bound together. I'll post a video or link a video within this one that talks about quarks and gluons a little bit in more detail than this one. But we talked about where all of our missing mass comes from, and the majority of our missing mass comes from the energy that's binding the up and down quarks together to form the protons and neutrons. Also, what I like to talk about is, although there are in our Regents reference table only 6 types of quarks, which make up baryons and mesons, and then we have our leptons, electrons, and neutrinos, there are other subatomic particles that we don't talk about in Regents physics. So just to give you an idea, under mesons, there are pions, kaons, and ettas. And if we scroll over under the lifetimes of those particles, we could see that they don't exist for a long time because they're very unstable. If we look at protons, we could see that their life expectancy is stable, which means that they are going to last for a lot longer period of time compared to the other ones, which is why we study those more frequently. But we also have lambda, sigma, chi, I think that's pronounced, omega. And then if we look at electrons, muons, and taus, we could see that the reason why we are composed of electrons versus muons or taus, despite having the same charge, they are not very stable in terms of their lifetime. And also they do have different masses than the electron. And then the neutrinos, we can also see that they are stable, and there are 3 different flavors, and we say that they are massless. So all I'm showing you here is that there are more particles than discussed in Regents physics that do exist in nature. And then lastly, if there is an antiparticle for every particle, that means for every up quark, there must be an antiquark. And we call antiquarks squarks. For every lepton, there must be an antilepton, and those are called sleptons. And for every force carrier, there must be an anti-force carrier, so an antiphoton or an antigraviton, and those are called SUSY force carriers for supersymmetry. And the last particle that we'd like to talk about is the Higgs particle, or the Higgs field. The Higgs particle in the Higgs field is what gives particles mass. So the particles that are affected or experience the Higgs field, what it does is it slows them down, and by slowing them down, they are then allowed to have mass. So photons do not interact with the Higgs field, and therefore they do not have mass. But quarks and leptons, they do interact with the Higgs field, and therefore they have mass. This idea was first proposed in 1964, and the Higgs boson was finally discovered in 2012 at the Large Hadron Collider. I'll also attach a video, or link to a video, that goes into more depth about the Higgs field, as well as quarks and leptons. And that's it for this video. Thank you for watching, and I hope you found it useful. See you next time.